Hi there everybody, this is Chee-Wee here. This video presentation is going to be talking about the diagnostic test methodology. I know that in week 8 for the homework assignment, some of you are having trouble doing calculating the confidence in determining if a change observed in the patient is real. So what I'm going to do is go through some of these concepts and then work step by step towards how to calculate the conclusion of the homework itself. But before that, we will need to be able to define and learn about some key concepts and definitions so that you understand what they actually mean. So before we do that, as I said, we need to learn some key concepts. And some of these key concepts are what's called accuracy statistics. Specifically, we're talking about sensitivity and specificity of a test. I'll define that in the later slides, but what they essentially try to find out is how accurate a test is or an outcome measure is in determining if someone has actually improved, or in some circumstances when used in diagnostics is used to determine if someone actually has the disease or a particular condition. And then we're going to learn how to obtain these statistics from published research papers, use them, and then be able to apply them to calculate the percentage or probability of how confident you are in determining a improvement observed in your own individual patient, whether that particular change you're observing is real and how confident you can be about that. So the two basic concepts are sensitivity and specificity. So for sensitivity, there are two things. Firstly, there is the real world where there is something that we probably as clinicians don't know, but the patient has probably has actually improved or not. So it's something we cannot observe, but let's pretend that the patient has actually improved clinically. So in that particular circumstance, when we apply the outcome measure or the clinical measurement, and the outcome measure or the test says that the patient has improved, that means that the test has accurately predicted and measured that the patient has actually improved. In this circumstance, when the patient really improved and the test says the same thing, it's called the sensitivity of the test. In the opposite scenario, when the patient has actually did not improve, so what has happened is that for whatever reasons the patient has not responded to your treatment. When you apply the outcome measure or clinical measurement, the test that you actually apply also says that the patient did not improve. Beyond sensitivity and specificity, there are circumstances when the test has demonstrated it is actually not as accurate as you think it is. In these circumstances, we call them diagnostic errors. Okay, so imagine the first situation when the patient has actually improved. However, when we apply the outcome measure or the clinical measurement, the outcome measure actually inaccurately thinks and measures that the patient hasn't improved. So we know that that's inaccurate. So in this particular circumstances, when the patient has actually improved, but the test says that the patient hasn't, it's called 1 minus specificity. There is another error, another diagnostic error, which is the opposite of 1 minus specificity, is called 1 minus sensitivity. So in this circumstance, the patient did not actually improve. However, when we administer the outcome measure actually says the patient has actually improved. So that's inaccurate. Okay, so this is the second error. If we were to put all these different errors and accuracy statistics into a table, and what we usually do is use a 2x2 matrix or a grid to represent it. So as you can see, the very top row says that ask the question, did the patient actually improve? So this is what we know in real life situation, that the patient, yes, the patient has improved, or no, the patient hasn't actually improved. And then on the leftmost column, there is a question is being asked that says, what does the test say? And this is the part when we administer the outcome measure, and the outcome measure then tells us whether it has measured an improvement or not. So this is what the clinician has administered. As you can see, if the patient has actually improved and under yes, and also when we administer a test there is a yes and improvement, that is called a sensitivity, which was what we tried to define. And if you look at the lower right hand corner, that is where specificity actually sits, where the patient actually did not improve and the test confirms that. And then we've got the other two errors sitting in between. So from the clinician's point of view, what we can only do is judge whether a patient has actually improved by what the outcome measure says. And the percentage of patients that we see that has improved is what's called a positive predictive value. How do we calculate this positive predictive value? Is to take the number of people who um, after administering the test shows that they have actually improved on the test, and then you divide that by the overall people who has whether they have actually improved or not, but still says but the test still says that they have actually improved. Okay, so this is what's called positive predictive value. Now the problem with this measure is that in order to get positive predictive value, we need the sensitivity of the test, which we don't know just by administering the outcome measure. Therefore, we need past research in order to get this sensitivity value. The same is true also for when we calculate the negative predictive value. So now we'll go on to talk about the negative predictive value. In order for us to do that, we need to actually look at the bottom row, which is the one highlighted in yellow in the 2x2 matrix itself. When I administer the outcome measure to the patient, all of them, the score that they obtain would indicate that they actually did not improve. However, as similar to the positive predictive value, there is one value that we need to know in order to calculate the negative predictive value, that's specificity. And again, we can get that from past research. Now, based on that, we're able to calculate the people who actually did not improve, and the test confirms that they did not improve. And then we divide that by the total number of people who got tested negative on the test. And then we can get the negative predictive value. Let's now try to apply some of these concepts to the homework that we have. In the case scenario that I've given you, I have asked you to pretend to be a clinician who is seeing a patient with frailty and reduced mobility. So over a 2-week period, we have provided some exercise to improve the patient's mobility and functional muscle strength. At the end of the 2 weeks, at the beginning of the 2 weeks, you administered a timed up and go test to see whether to see the baseline of what the patient has on this particular outcome measure. At the end of the 2 weeks, you then reassess the patient again using the same outcome measure. What you found is that the patient has achieved an improvement of 11%. Now, what I wanted you to find out was how confident can you be that the 11% improvement is actually accurate or real improvement. So a lot of times what we're trying to do is we're simply trying to find the positive predictive value and not take what we see in front of us as an absolute thing. So the 11%, yes, the patient has actually improved by 11%, but then again, we need to know how confident we are. So now, in order to in order to actually calculate the positive predictive value for this particular patient, you first need a research study that provides you with some useful figures. Actually, what we are really interested in are the accuracy statistics, which is your sensitivity and your specificity. In this case, I found the article by Van Ursel, 2008, to help us with this particular calculation. Now, firstly, you will need to extract some information from the research paper to fill up this particular 2x2 grid that we have actually constructed. You can see that this 2x2 grid is exactly the same as what we used before when I was trying to define for you what sensitivity and specificity is. The only difference is that now, instead of asking whether the test is actually measuring improvement, what we especially ask is, what does the test say for an improvement of more than 9%? And the reason why we chose 9% is because the research has defined an improvement to be at 9%. If you look at the slide, what I've done is I've simply done a screenshot of that bit of the paper actually in the abstract, that we can actually pluck out some of the figures that we need. The two figures that we need are the sensitivity for the time up and go test, as well as the specificity of the time up and go test. In this case, the TUG sensitivity is 93%, highlighted in pink over here, and the specificity of the TUG is 34%, highlighted in green on the slide. And we simply take these two percentages and plug it into the appropriate boxes within the matrix itself. The next thing we need to find out is how many patients are there in total. From the paper, we know that there are altogether about 85 patients in the research. And out of this 85 people, it has been found that 26 patients actually improved. Therefore, the 26 will be placed under the yes, the patient has actually improved, okay, in the third column, and the rest of the patients, which is about 59, will have been put under the did the patient actually improve? No, they did not. So that's 59, and that's where these two figures will go to. Now, we already said that the numbers that we need to calculate our confidence in knowing this improvement is real or not are the sensitivity and specificity. If you were to do this for your own clinics, for your own patients, what you only need are these two figures. However, in order to show you how to fill up all the numbers in a 2x2 matrix, and what I'm going to do is I'm going to work out all the different numbers within the other boxes that we have not filled in together, and I'll show that in the next few slides. We talked about 26 patients in the paper, in the research study itself, that has been shown to have an actual improvement. So this 26 people, if you divide it by the total number of people, is actually what's called the prevalence of the improvement, and in this case is about 30.6%. Now we will probably be able to use this concept later on when we are calculating the probability of our own how confident we are in determining if our patient has actually improved really by 11%. Now, what I've done is also I've filled in the other two boxes where the 1 minus specificity and 1 minus sensitivity sits. It's quite simple. If you look at the column that has been colored blue, so we already know the total, which is 26 patients has actually improved, and we also know that the sensitivity of the test is 93%. So if we calculate 93% of 26, that will give us 24 patients, and that allows us to fill in the box below that, okay, which is simply 2, because 24 plus 2 gives you 26. Now we can do exactly the same also for the specificity for the orange columns. So instead of using sensitivity, we can now use the specificity to calculate all the missing numbers. Because we've filled in about most of the box, now we have got all the information required to fill up the entire table. As you can see, I filled up the very last column with all the appropriate numbers. The last column is simply a total of that particular row. So let's say if we look at the pink row, which is the test saying yes, the patient is improved by more than 9%. The total is simply 24 plus 39, which gives you 63. The same applies when we look at the no row, where we add up all the blue boxes, which is 2 plus 20, and gives you 22. To double check if this is correct, add up the total to give you the grand total. 63 plus 22 is 85. Double check. If you look at the last row, 26 plus 59 also gives you 85. So that confirms that all the numbers all add up and it's consistent with each other. The only issue is that because these numbers are plucked from the research itself, and when we do research, we are really looking at whole populations. When we apply it to our own individual patients, there are some additional information that we need. Otherwise, the numbers would not be applicable to how we predict the accuracy of our test or how likely someone has actually improved. So, the additional information that we need is our educated guess at how likely the patient has actually improved. Many times, this is very hard to know. If you don't really know, then the best educated guess that you can make is simply that the likelihood is 50% that the patient has actually improved. What this simply means that there is a 50% chance that the patient has actually improved or not improved. Okay, that means that even without your treatment, the patient will have improved simply by chance. Could be because they are naturally recovered. But if by your own personal experience you feel that usually at this stage, like the likelihood that the patient has improved is about 75%, then you can make this educated guess to be 75% instead. So now you have to create a 2x2 grid for your own clinic. In this case, we have simply copied over the grid that we did for the research and just put it here. It's exactly the same. We already know that based on the research that the sensitivity is 93% and that the specificity is 34%. And we also know that 50% of the patients has actually probably improved. So we can actually input some of these numbers in. So these are the numbers that has been put in. So based on the assumption that we've seen 200 patients, so 100 patients will be under the column where it says the patient has actually improved, and 100 will be under the column that says no, the patient has actually not improved. We fill in the 93% into the sensitivity and into the sensitivity box and 34% into the specificity box. If we were to convert that into actual patients, because the total number of patients under the yes, the patient has actually improved is 100, so 93% of that would give you 93 patients. The same applies for the column that says that the patient has did not actually improve, and because the specificity is 34%, you convert that into number of patients. That gives you 34 patients. Using the same principle that we did for the research, we can now put in all the numbers into the different boxes, and this particular slide will show you actually all the different numbers, and they all add up to a grand total of 200 patients. We can now do the very last bit, which is to proceed on to calculate our positive predictive value, which is what we need. The formula for the positive predictive value is as indicated in the book. in Riddle and Stratford is A, which is 93 over here, divided by A plus B, which is 93 plus 66, which gives you 159. Taking that proportion, we multiply it by 100 to convert it into the percentage, and that gives us 58.5%. So the positive predictive value of our of for this particular patient, whether that the patient has actually improved by 11%, is 58.5%. Going back to our homework again, let's revisit the question. The question was, how confident are you that 11% improvement is accurate? So we have calculated a positive predictive value and it gives us 58.5%. The answer therefore should be that we are 58.5% confident that the improvement of 11% is accurate. So the next question you want to ask me is that good or is that bad? Actually, that's not very good, because our confidence of the patient actually having that 11% improvement is only slightly better than chance, because 50% is is by chance. So if we're only about 8.5% more than chance, that is not very good. We would want to be able to improve our confidence by more than that. So it has got lots of implications, but for now we will not go into that. But I hope that this short video will be able to help you to understand some of these quite difficult concepts. But if you need to, please do revisit the Riddle and Stratford book chapter again and reread some of these concepts, because they are quite important.